Hello, everyone. Sorry for not being here in person. Hopefully, we'll get to do this again next year. In the meantime, here's my presentation on how LEDs got out of control. And I think the first ones are free, and then it ends up being a very expensive hobby. So those are all the links you'll want if you want to look at all the projects. You can go back and rewind to this little slide, and it will have the links to everything else you need. Here specifically is a whole story of basically this talk in a much longer page if you'd like to have details. So let's start with the first, one of the first Arduino minicomps, which had a slightly improved board. It had some shiny thing that had different colors on it that you can see on the screen. And then it had an LCD that I wrote a glue driver for. That one I made a menu for where I could actually select the color components for the LED and how quickly it would pulse using the potentiometer here. So that was my first project. As I said, the first one is free. I thought, well, if I get a few more of these, I get this little guy that was super cheap. The problem is that they didn't have enough input to control all the LEDs, so they were controlled line by line, line scanning, and you could select on each row which color you wanted on or off. And by flipping the colors very quickly on or off, you could create color components. And I wrote a driver for that, which is shown in this picture. That kind of burned at Christmas, but hey, it was interesting, a good little experience, and actually related to what I'm doing now on the bigger panels that I'm currently using. All right, so this brings us to this project from a later mini-conf in 2016. That was supposed to take care of your plants and see how your dirt, humidity, temperature, and your dirt to see how much watering you were doing. It seems kind of obvious to add a new pixel ring to that because bling, I guess, and bling is good, right? So blings make smiles. So that was probably my first set of NeoPixels. A lot of fun to program. I had more fun with NeoPixels than actually the main reason to use that board. Sorry, guys. And then the following year, well, if you have a lot of pixels, it actually creates a screen, and that's what a TFT is. So I got to play with programming that, made an entire interface. But as you'll notice, there's two more NeoPixels there. I guess no matter what you do, NeoPixels end up in the projects that you get in the miniconf. So I think the hint was pretty clear. If you have a few more than two, you end up with a string. And if you have a string, you can do cool stuff. So that's what this is. I made an outfit that had four NeoPixel strings on the arms and legs. So those were all controllable independently, and I had moving patterns on them. And in the middle of the shirt was just LEDs that didn't change. They could change color, but they were all together. So you can see the difference between the NeoPixels here and these guys that are all the same. And that's all the circuitry that I made for that. So that was back in 2017. That was fun, and it kind of got out of hand a little bit. So just, I guess, a little bit over a year and a half later, I had issues with the previous shirt where washing it was a problem because everything was glued onto it. And yes, so that was a problem. I figured, well, what if I make the LEDs removable? I should probably put a panel or something. And by then, you can buy those NeoPixel panels. There was 8 times 32, so I had 3 of them in parallel. And I made a panel to go in the front of the shirt and the back. And of course, now I got a matrix out of it. So that was the next version. I have a whole page that explains kind of what I can do with it and how it was made and built and how it goes. You can see the pixels are actually still reasonably big. They're about 1 centimeter. The wiring isn't terrible. This shows 1 pixel being replaced, a pixel that died. All the pixels are in line, so if 1 pixel dies, everything after that stops working. But even for my bad soldering skills, it was manageable. Now, yeah, this happened. Someone who hates me gave me 4,000 pixel, or a few more than 4,000. So the obvious thing was to do a 6464 matrix. That burned an entire week of my life. Do not do this. It's extremely stupid. And yeah, it was a lot of work to lay them all out. The output looked like this. it was very nice, and then you'll see the next version of my shirt next to it, and you can notice they're running the same pattern, and that's kind of the general idea. So this is where frame buffer GFX came in. After doing some work with different pieces of hardware, I realized, hey, I need to have a common library that controls everything so that my code can run everywhere the same. So you can see, some really weird mappings, like this would be a user of mine did those using digits and made with NeoPixels, and he did a custom mapping so that you could write as if it were a rectangle of pixels, but it would actually end up in the right pixels in the middle using that mapping. The more typical mappings are, these where you have pre-made matrices like these, and they're daisy chained, but as you can see now, the numbers are not in sequence, and that's what NeoMatrix does. It does a mapping of pixel 8, 8, and it puts it in the right place since the ordering has to be changed. So going back to this library, so now I have the same code, and I can be running either on NeoPixels using NeoMatrix or RGB panels running on top of Smart Matrix. That was using an ESP32. You can also do that on a TZ. And so I made a glue library that goes on top of that, so that way I can use frame buffer GFX on both. So I'll show you a little bit of a graph. ASCII art is the best, obviously. Frame buffer GFX is basically the frame buffer, 24 bits per pixel. It talks to Adafruit GFX underneath. It can emulate, it can be compatible with LED Matrix, which is a different API on top of NeoPixels. So if you write your code for NeoPixels using LED Matrix, you can actually rerun it on everything else that I support. And there's also the Fast LED API, which is supported. So this is where cool, because you can write a Fast LED code, but then by going through Frame Buffer GFX, you can run it on anything underneath that is not NeoPixels. So on the top side, of course, you do have NeoPixels, then you have Smart Matrix for RGB panels. Those are TFTs, so I wrote a glue library to talk to TFTs. Underneath, I realized, hey, that would be really cool if I could run my code on Linux, because I would write it so much quicker. I can run the GDB, I don't have the compile upload cycle, and it's just win all around. The next reason, of course, was to run on our Raspberry Pi, because there's that really good driver, RPI RGB panel, that allows you to run a lot more RGB panels quicker than you can do with smaller chip like Teensy. All right, so I'll go quickly. So this is basically my shirt running RGB panels. Running a higher resolution that's 6496. And yeah, if you go back to those pages, you'll get a video that shows you all the patterns running on it. I have to go quickly. So now this is the exact same size in RGB panels. The pixels that used to be 4 millimeter are now just 2. And this is 128 times 64 per panel. And you can see here there's an Raspberry Pi with a Electro Dragon board on top, and it has 3 different channels. So it's running those panels in parallel to refresh them at full speed, because they're basically full refresh panels. So you have to keep refreshing the lines over and over again. And that's how you emulate the colors, a little bit like the first 8x matrix that I showed you. So I wrote, again, the glue library to make this work. So now I have my Arduino code running on top of Raspberry Pi with no rewrite on a completely different piece of hardware. Then I told you about Linux. So I can definitely run that code on Linux as shown here. Let's see if I can play it for you. There we go. So this is the ESP32 running on its own RGB panel. It is connected to Linux via a USB port, and Linux is running the same code, but run independently. So it's getting the command through Wi-Fi right now from the ESP32 saying, hey, I'm running demo number whatever. And then it gets to Linux, which says, oh, okay, actually run the same demo. And it renders it locally in a resolution that's 4 times as big. So this is how I was writing and debugging the code very quickly. From here, I also made some really big panels. Okay, this is starting to get a little bit expensive. The panels on the left were actually free. The ones, because they were returns, they were not compatible at the time. But with the people who bought them, let me see if I can actually play this video. The play button is being hidden. Let me see, click that. There we go. So the ones on the left were free. The ones on the right are 64,128. Those panels actually cost $50 a piece. So if you do the math, it adds up a little bit. But look at this. Isn't that gorgeous, right? So this is basically what you can do when you go bigger. All right, but back to my shirt. So the idea is, you can see on top of the screen, that was my old panel. That was 6496. The new one is now twice as much, 128 times 192. I say twice, it's actually 4 times the number of pixels. So basically, the ESP32 is still getting the commands of what to do, and it's rendering now to a panel that will not be connected. It's then connected to the Raspberry Pi, and the Raspberry Pi will be doing its own rendering, and the resolution that's 4 times bigger. So some demos are the same, like these, and they're being rendered separately on the Raspberry Pi. So this is going to be the new shirt I'm going to be wearing. All right, and I think that gives you a reasonable idea of what it looks like. Again, the idea is that it all runs on top of Frame Buffer GFX. It's all the same code. It was written for Arduino. Now it runs on ESP8266, ESP32, Teensy, Raspberry Pi, and Linux. And the best part, again, on Linux is I can just debug the code and do it on my laptop without having to do the upload cycle. So there you go. If you have any questions, hopefully I'll be here to answer them.